Today's goal is to find the inverse of a function. Yesterday we were verifying and even proving whether or not two functions are inverses, but today we're going to come up with the function that we know is the inverse of a given function. We're not given pairs like yesterday to say yes or no, are they inverses or not. We're just given one function and we have to find its pair, the inverse function. Now we've been talking about inverses a lot. We can think of inverse functions in two equivalent ways. One way to think of a function and its inverse are the function that undoes the other function. So for example, yesterday we showed that if I want to prove two functions are indeed inverses, you have to prove that they cancel out. That means that both f of f inverse of x must be x. You should be able to cancel out the function and its inverse, whether you're substituting that value into an inverse first and then the original function, or into the original function first and then the inverse function. The other way we like to think about inverse functions is saying whatever the domain and range are for a given function, the inverse function is the function that switches its inputs and outputs. This is sort of the way we like to think about inverse functions that'll help us today. This is a topic we learned a couple units ago, but today we're just practicing on functions we've learned since we've last visited finding an inverse function. So let's take a look at our first example. We have f of x or y equals the log of x plus 2. If we want to find the inverse function, I have to think about switching the x and the y value. So that leaves us with x equals the log of y plus 2. I'm going to put parentheses around the y. We should assume that the 2 is not actually part of the log function unless there are parentheses there. They would have to show you parentheses like this to make the 2 a part of the log function. So I'll put in parentheses just to really emphasize 2 is not a part of the log function. Okay, all I've done is switch the inputs and the outputs. Now, of course, this looks goofy because it's not solved for y. So let's solve for y. We can subtract 2 from both sides. And now, if you remember, this unwritten base is 10. So we can put both sides, write both sides as an exponent of base 10. And that's handy because these are inverse functions, so they cancel out just to give us y. Of course, the shortcut is just rearranging the terms. And then I'm going to go back to inverse function notation just to really emphasize. 10 to the power x minus 2 is the function that undoes this original f of x, log of x plus 2. Okay, let's find this inverse. Again, all I need to do is recognize this is the same thing as y. I need to switch x and y, and then solve for y. Okay, this time I'm going to solve for y by putting both sides to the e power. Oh, I'm sorry, by taking the natural log of both sides. Because the natural log and e to a power are inverse functions, they'll undo each other. So I'm left with y minus 4. Now I can just add 4 to both sides. And then I'm going to really use this function notation to emphasize I'm finding the inverse of my original function g. One more function just to get the hang of it. Then we'll switch gears just a little bit. Y is equal to the inverse sign or the arc sign of x plus 1. I'm going to switch the x and the y values, take the sign of both sides, you'll notice that I'm always using an inverse function to get something to cancel out. That'll allow me to isolate y. And then I really like going back to that function notation just to emphasize that these two are a pair, right? These are the two functions that undo each other. Okay. One more example for today. Find the inverse of a function and then verify by composition that your answer is the inverse function. So we're doing two things. We're finding and then we're verifying. Well, we know to find that pair, that inverse function, we just switch the x and the y and then solve for y. You can leave the left-hand side as x minus 1 over 2 if you like. I like to write it as two different terms so I can just remember that both the x and the 1 are being divided by 2. And so now I have this y to the 7th. Well, when I had an exponent before, I took the natural log of both sides, but that's because my variable was in the exponent. This time my variable is not in the exponent. My variable is the base of the exponent, y. And so I need a different technique. There are two different things you can do at this point. One thing you can do is take the 7th root of both sides. And so you have y is equal to the 7th root of x over 2 minus 1/2. Or equivalently, at this point, you've got x over 2 minus 1/2 is y to the 7th. Taking the 7th root is exactly the same thing as taking both sides to the power 1/7. It's just written in a different way. So x over 2 minus 1/2 to the 1/7 power is equal to y. These two functions are equivalent, meaning they are exactly the same. It's just a different way of writing it. So pick your favorite, use either one. And then again, we'll just call these f inverse. Okay, you can use either one, whichever you're more comfortable with. Keep in mind, you cannot distribute this exponent. You'd have to put it to get to a root. So neither expression, neither this radical expression nor this exponential expression is easy to simplify. Okay, so we're done finding the inverse. Now we need to verify that these actually are inverse functions. Well, we learned how to do that yesterday. We need to do some function composition. So let's put this function, the 7th root of x over 2 minus 1/2, into our function f of x. So here's 2x to the 7th plus 1. Now the 7th root and exponentiating to the 7th power, those are inverse functions, so they'll cancel out. So we have 2 times x over 2 minus 1/2 plus 1, which gives us 2x over 2 minus 2 over 2 plus 1, which indeed is x. We have to also show that f inverse of f of x is also x. We've got to be able to cancel out these two functions, whether we're first putting it into the original or first putting a value into the inverse function. So let's see if this actually works. We'll take our original function here and substitute it in. Again, use the 7th root or to the 7th power. Either one is fine. So we have 2x to the 7th plus 1 over 2 minus 1/2, which gives us the 7th root of, this is 2x to the 7th over 2 plus 1/2 minus 1/2, which is the 7th root of 2x to the 7th over 2, right? These guys will cancel out, which is the 7th root of x to the 7th. These guys cancel out, which is x. And so now we are done. You can use a little square and fill it in, or you can use QED as sort of your symbol of I have come and I have proved what I have intended to prove.